So we're going to talk now about representing negative numbers in binary. And it's a little bit different than you would expect. And it only makes sense in the context of variables in your computer programs. So in C language, we could declare a char variable. That's the smallest one there is. In C#, it would be called an S byte. All of these are the smallest data types in the language. And in Java, a byte. So each of these has 8 bits of space. I'll draw the spaces. 1, 2, 3, 4, 1, 2, 3, 4. 8 bits of space. And each of these can store positive and negative numbers. So to store negative numbers, we need some way of indicating that the bits in these 8 bits are not representing a positive number. And we do it by the most significant bit is called the sign bit. So if the sign bit is 1, then we have a negative number in the remaining 7 bits. And if the sign bit is 0, then we have a positive number in the remaining 7 bits. So one of the bits is used up, not for data, but for indicating whether this is a negative number or a positive number. So far, so good? Well, what I would like to do is ask you to get a pencil and paper and do this along with me. Do some negative number conversions. And if you do that, then you'll know how to do it. And if you don't, then you will have just watched a video. So I'm going to make a new data type which doesn't exist in any language, and I'm going to call it a nibble. That's part of a byte. Get it? Okay, a nibble, N. And in a nibble, we have only 4 bits of space. And I'm making this tiny one for the purpose of explanation. It's just easier to get around with. So this most significant bit is going to be the sign bit. So if it's a 0, then we have a positive number. And if it's a 1, then we have a negative number. So you already know how to represent a positive number. So there's 0, 1, 1, 1. And that's 7. Positive 7 is the largest number we can store in a nibble. So the positive numbers are easy. You just look at the most significant bit, which is the sign bit, and if it's a 0, then the remaining bits are a positive number. So what if we wanted to represent a negative number? So let's go over here and put our map. 1, 2, 4, and I'm going to put 8 here, and that's the one that we use as the sign bit, the most significant bit. So let's start out by saying this is the number 5, 1, 0, 1, the positive number 5. And I'll put a 5 here. Now I want to find out what is the bit pattern, what are the 4 bits that would represent negative 5. Negative 5. And this is how we're going to do it. The first thing we're going to do is invert all the bits. 1, 0, 1, 0. This is called the ones complement. The ones complement. And that's complement spelled with an E, not complement spelled with an I, like you look very nice today. That's a compliment. A complement with an E here, complement, is the inversion of what we have. So the ones complement is the first step. And then we're going to add 1 to the ones complement. So let's add 1 to the ones complement. 1 plus 0 is 1. There's 1, 0, and 1. Okay, so I'm claiming that this bit pattern, 1, 0, 1, 1, is negative 5. It doesn't look like negative 5. The 1 is the sign bit. The first one is the sign bit. And it might look to you like, well, that's 3, so this must represent negative 3, but it doesn't. how are we going to prove it? How will I prove it to you that 1011 is the bit pattern for -5? Well, -5 plus 5 should be 0. That's not too hard to believe. So let's take the positive 5 bit pattern 0101 and add it to what I'm claiming is -5. Okay, let's add these together. 1 plus 1 is 2, which in binary is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. But we've only got 4 bits to work with. So this bit out here fell off on the floor, and we have 0, 0, 0, 0, which is 0. Okay, so you're asking me, why on earth would we have done this? Why would we represent a negative number in this complicated way? And I don't have a really good reason without a long explanation, but it works out that this is the way that it's done, and it's originally done this way because of making the hardware run faster and do arithmetic faster. Okay, so let's do a couple more of those. I'm going to erase all of this. Let's put a bit pattern, a positive number. How about 7? And what is the bit pattern for -7? First we'll invert them, and we'll get the 1's complement. 1, 0, 0, 0. That's the 1's complement. And then when we add 1 to the 1's complement, we get 1, 0, 0, 1. And I forgot to tell you that this is called the 2's complement. The 2's complement. So 1, 0, 0, 1, I'm claiming is -7. The sign bit is turned on, and there's only a 1 at the end here. It doesn't look like -7, but we'll prove it by adding what we know is +7. 1 plus 1 is 0, carry 1. It always works this way. 0, carry 1, 0, carry 1, 0, carry 1, and that 1 falls off on the floor because we only have 4 bits of space. Okay, so negative numbers are represented as 2's complement. Let's erase that out of there and go back to, I'm sure there's an easier way of doing that. Suppose we have a bit pattern 1, 0, 1, 0. That's a negative number because the sign bit is turned on. What negative number is it? So I'll just put a question mark here. It works the same in both directions. If we want to know what is the magnitude of that negative number, we're going to do the same thing. Take the 1's complement, 0, 1, 0, 1. There's the 1's complement of whatever that number is, and then we're going to add 1 to it. So 1 plus 1 is 0, carry 1, 1, and 0. And this we have the number 6. 1, 4, and 1, 2. So there's the bit pattern for the number 6, and we know that we must have been starting out with 1, 0, 1, 0. This must have been -6. And we can prove it again in the same way. 1, 0, 1, 0. 0 plus 0 is 0. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. And this 1 falls off on the floor. So The bit pattern, when you want to find out what value do you have, what negative number is that, you take the 2's complement, and that is the magnitude of what negative number we started with. Okay, so we're not doing this in 4 bits ever. We're doing it in 8 bits or 16 or 32 or 64, depending on the data type that you've declared. And in all cases, the most significant bit is the sign bit. I'm going to erase some of this. (16, 32, 64, 128). So we don't have a nibble anymore. If we were working in Java, we would have a byte or 8 bits of space. In C, we would have a char. That's a little bit tricky because a char in Java is 2 bytes of space. But in C language, it is 8 bits of space. Did I say bytes? Darn it. Let me do this again. If you declare a byte in Java, it is 8 bits of space. A char in C is 8 bits of space. And an S byte in C#. So internally, all of those are the same. And it means that this most significant bit is the sign bit. So let's just throw in some numbers, some bits in here. Now, is that a positive number or a negative number? We know it's a negative number because the sign bit is turned on. What negative number is it? Gee, we don't know, but we can find out. We can find out by taking the 2's complement of these bits. So let's flip them all. 0, 0, 0, 1, 0, 1, 0, 1. So there's the 1's complement. And then we're going to add 1 to the 1's complement, and that will give us the 2's complement. So remember, we're trying to figure out what negative number is that. 1 plus 1 is 2, which is 0, carry 1, and then these just all fall down. 1, 0, 1, 0, 0, 0. So what number is this? A 16, a 4, and a 2. So it's 22. This is the bit pattern for the number 22. So this bit pattern that we started with is the bit pattern for minus 22. And we could prove it. Let's add minus 22 to 22, and we should get 0. 0 plus 0 is 0, 1 plus 1 is 0, carry 1, 0, carry 1, 0, carry 1, 0, carry 1. And now this is the one that falls off on the floor because we don't have room for it. So 22 plus minus 22 in 8 bits of space is 0. So in your larger data types, in int and long, depending on what language you're using, it's always the most significant bit that is the sign bit, whichever one that is. So in this one, where we use an 8-bit data type, the most significant bit is the 8th one, the 128th place. Let's go back to a nibble just for a second, and I'm going to show you something that's kind of fun. There must be an easier way to erase this. I don't know how. So here's a nibble again, and I'm going to say, let's put a negative number 1000. So I know it's a negative number, but I don't know what negative number it is. So I'll put a question mark there. Let's take the 2's complement and add 1 to get the 1's complement, and then add 1 to get the 2's complement. 1 plus 1 is 0. 1 plus 1 is 0. 1 plus 1 is 0. Isn't this interesting? We have the exact same bit pattern that we started with. And this happens only once. In this particular case, when the sign bit is turned on and all the remaining bits are 0. So what negative number is that? When we took the 2's complement, we have the number 8. So this is the value -8, but we cannot represent positive 8, because if we have -8, the sign bit is turned on. This always happens. The largest negative number we can represent in this nibble is -8, and the largest positive number we can represent is 7. You always get one more negative number than you do positive numbers because of this odd circumstance where the 2's complement of the number is exactly the same thing as you started with. So this is -2 to the power of 3. And this is 2 to the power of 3 minus 1. So there's the range of values that you can put in a nibble in 4 bits. So we have 3 data bits in a nibble and 1 sign bit. So suppose we had an 8-bit data type. We would have 7 data bits. -2 to the 7 through 2 to the 7 minus 1. So there's the range of values we can store in a byte. And this works for all of them. All of the signed data types in all languages. You get one more negative number than you get positive numbers. In a short, a 16-bit data type, it's 2 to the power of 15, take the negative of that, up to 2 to the power of 15 minus 1. So there's the range of values you can store in a 16-bit data type. And for 32, it's -2 to the 31 through 2 to the 31 minus 1, and 2 to the power of 63 through 2 to the power of 63 minus 1. -2 to the power of 63 through 2 to the 63 minus 1. Isn't this interesting? When will this be important to you? Well, if you try to represent 128 in an 8-bit data type, you cannot. An 8-bit signed data type. And if you try to represent 2 to the power of 31, the positive number 2 to the power of 31, when you have a 32-bit data type, it won't work. So all of the time, programmers don't have to be thinking about what's going on in the bits, but at some point, the arithmetic will not work. You will make your numbers get bigger than they can fit in the data type that you're using, and you will accidentally turn on the sign bit. So what was a what was a positive number, if you just add 1 to it, sometimes you're going to have a negative number, and a large negative number, and the answer to your arithmetic won't make sense. So the person who understands this will be able to look at the bit pattern and find what was going wrong with the arithmetic, and the person who doesn't understand this will be stuck not knowing why the arithmetic doesn't work. So you don't have to be thinking about it all the time, but when something goes wrong, that's when this is important. Know that the sign bit can be clobbered. When your number gets too big, all of a sudden it becomes a negative. And that's not the answers that you want. Okay, that's enough working with bits to represent negative numbers.